Okay, let's get going with molecular formula then, please, which is on page 30. You might remember where we finished off last time was with empirical formula. Do you remember what empirical formula means?
Isn't that the last whole number ratio?
It absolutely is. So it's the last whole number ratio of
Ions within a compound, or atoms within
or we could just say elements. So some of them are going to be ions, some of them won't be. It'll only be ions if it's ionically bonded. It's going to be atoms of those particular elements if it's covalently bonded. Now, so we did say that, well, this is okay for some compounds in that if we had methane, for example, the empirical formula for methane is then the same as the molecular formula, because what is the molecular formula? What does the molecular formula tell us?
how it actually exists, and it's
Yeah.
the same as what's.
So this is the actual composition. And so yeah, like with my example here, my empirical formula for methane, my actual composition is the same. And so if I have something different, we think about, well, benzene is one of our examples in here. The actual molecular formula for benzene is C6H6. But if I were to work out the empirical formula first, what would I come up with for the empirical formula for benzene?
CH.
Just CH. And the most common way that we encounter these calculations for the molecular formula is that we've found the empirical formula based on percentage by mass, and we are then using that information to determine the molecular formula. So that's what we want to look at now, is to see how we can do these calculations. Now what we would find is, well, what we do is we calculate the mass of this, and it would be around 13, wouldn't it? And then we would be given the mass of the molecular formula. And we divide the molecular formula by the empirical formula. And if I we'll actually find that if we would know that we wouldn't know this. Okay, this is just an idea at the moment. But we would be given the mass, and we would be given the mass of, say, 78 grams per mole. This part, though, is always the same, that we're going to divide the molecular formula by the empirical formula. And if we did that with these numbers, we're going to get 6. That tells us that in actual fact there are 6 times as many atoms in the molecular formula compared to the number of atoms in the empirical formula, or moles. With this information, with the 6, we know we have to use it as the subscript. We can't just put the big 6 out the front. Why can't we do that? Why is that wrong? What does that mean?
That's how many particles there are all compounds.
Yeah. Particles is a good word. So what this means I've got that. I've got 6 CFs. Now that can never be right, can it? It should be H. I don't know why I put an F there. Anyhow. Why can't that be right? What's wrong with that? Apologies for my alphabet fail. What's wrong with that?
Isn't it just because that's like the amount of substance? It's not actually the combination.
Yeah, that is just how many. Yeah, that's not the correct way they're bonded together. But what is wrong with the bonding within it? Why can't it possibly be right?
Because carbon requires 4 electrons and it's only hydrogen only requires 1. So
Yeah.
they're not sort of.
So each of these carbons really needs 4 bonds filled, doesn't it? And it's only got 1. So this can't exist. So it's wrong. Because our carbons do need 4 bonds. Okay, so what that does mean though is that we have to use it as a subscript. Because that's telling me how many there are within the compound. Okay, so basically we did do that example, the worked example, where we found the empirical formula mass, and we found we were given the molar mass, and then we divide the molecular formula by the empirical formula. That's where I got the S from. I see. Does anybody want me to do another example of calculating the molecular formula?
Can you do it where the C and the H have different numbers?
Yeah, let's do the ethanoic acid example from the table below. So the way we would be asked to determine the empirical formula after having been given percent masses. Okay, that's the normal first step. But I'm skipping that step because I'm just going to use the values from this table. And I'm going to just assume that I figured out that my empirical formula was CH2O of this unknown. Okay? Now I just need to quickly do a calculation to work out times 12. Now the second part, I'm told to determine the molecular formula if it's 60 grams per mole. Okay, so this is the normal way that you would see it in that question. So what we have to do, step 1 in our answering, we have to work out what a mole of the empirical formula mass is. So for CH2O, it's going to be 12.01 plus 2 times 1.008 plus 16.00, which is 30.0 grams per mole. Okay, so now we know what the molar mass from the empirical formula is, and then we use this relationship here, where we're going to divide the molecular formula, step 2, divided by the empirical formula. Masses. 60.0 divided by 30.0 is 2. And then step 3 is we're going to then use this ratio within the compound. So in this case, we need to multiply everything by 2. Get C2H4O2 is then our final answer. Okay, does that make sense? Now, so we've talked about this being wrong. The other way, I guess, that sometimes students make mistakes is by getting these around the wrong way, doing the empirical formula divided by the molecular formula. You'll know that you've made a mistake because, look, if they're the same, like it was with methane, it makes no difference. You'll see that the numbers are the same and you won't even worry about doing a calculation. And if you came out with something like 60, you'd probably not do a calculation either, because you'd be able to just look at that and see that it's done. You're really only going to need to do a calculation step, perhaps if it's less obvious to you, what number to use. But if you've got these around the wrong way, then you're going to end up with a number less than 1. Can't have a number less than 1. We can't have it any less in our molecule than we had in our empirical ratio, can we? So we can't ever end up with a number less than 1. And so we would know we've made a mistake. And then we could just have another look at it and turn it around the other way. Okay, so there's a table of a comparison of some different molecules on page 30, where you can see the relationship there between the empirical formula and the molecular formula. The smallest ratio is 1 to 1, where basically the empirical formula is the same as the molecular formula. It can only go up. From there, the molecular formula can only go larger from that position. So, there are some questions then on pages. Well, there's also, like I said, we've already done a worked example. Questions 44 to 48 combining together empirical formula and molecular formula, which is the